Thank you. So first let me thank everybody who put this together. It's a great lineup this week, and I'm very excited to see all of the talks. I know we all just had lunch and we're just getting started, so this talk is going to be a little lighter. It's going to be some fun geometry problems, and the eagle-eyed amongst you will see persistent homology when it sneaks by. Sure, sorry, I realized I'm talking into this thing and I expect it to be filling the room, but of course it's not. So, excuse me. Okay, so you'll see persistent homology if you look for it, but I'm not going to talk about it. This is just geometry. And of course I have to thank my collaborators. Joshua Cruz, Vladimir Itzkov, and Bill Kronholm all helped me put all of this together. And if you should discover that you think that the intersection of algebraic topology and neuroscience is an interesting place to think about things, I have a complete list of every paper published on the subject on this webpage. You can go there and find it, and it'll give you a flavor for what people are doing. So, also, that might suggest to you that it's small. It is currently a very small intersection, but consider this an advertisement. Every topologist should be at least considering neuroscience applications because it's such a natural thing to do. And I'm just going to try to convince you of that. So let's talk about some actual neuroscience. This guy on the left is John O'Keefe, who won the Nobel Prize for Medicine a couple of years ago. And he won it for the following, this is a tremendous picture of him because he smiles in literally every picture. And I found this terribly intimidating picture of him. But he's always grinning, and then, so what did he do to win the Nobel Prize? In the mid-'70s, he took a rat, much like that one, and he put an electrode deep in its brain in the hippocampus, which is a very, very deep area in the brain, very difficult to get to, so this was cutting-edge neural recording, okay? And he let the rat run around inside its environment. It's just a square box. And so this black line here is the trace of the animal moving, and those red dots are places where one individual neuron in the hippocampus, deep, deep in the brain, was spiking. Okay, so that's phenomenal, because it's pretty clear what's happening there. Just to be super clear, I'm going to deconvolve it. Oh, no, I'm not, because I'm missing that slide. So look, there's a hot spot, right? There's a location in the room where that one neuron is firing, in spite of the fact that you're not getting direct sensory input from anything. Okay, so that's just an amazing thing to discover, and so of course Nobel Prize for Medicine later. But he essentially launched this entire idea that there are deep brain areas which are encoding these conceptual things in a decodable fashion. So what this is called a place field, and what you can do is you can just sort of construct this heat map, which is a function which describes the location in the environment. The white line is, my cartoon animal walking around, and as it moves around, a neuron which has this particular what you call receptive field is going to fire with probability based on the temperature at that location. Okay, so this is what his Nobel Prize is essentially for. It took him about a decade to convince anybody this is true, but it's now thoroughly accepted. And then once you've got one, you've got many, because there are lots of cells in there. So these place fields form a cover of the environment. And you say to yourself, oh, I've seen covers of things somewhere. Where have I seen them? Probably topology. So that's why I'm here. So right, so the cells literally cover everything. So we have an open cover of the environment you're standing in. You should be able to reconstruct the topology of the space just looking at this, and it turns out that you can from the neural data. But in case that does not sell you on this, let me show you the other people. Maybrit and Edvard Moser, who co-won this Nobel Prize for their much more recent discovery. Right above the hippocampus, there's an area called the entorhinal cortex, slightly closer to the surface, which has these cells which fire like this. So these don't fire in a particular location, they fire in a hexagonally periodic tiling of the plane. And if you have taken a graduate topology course, one of the first things you ever did was you said, well, if I have a hexagonal tiling of the plane, I take the fundamental domain and I sew it up, what do I get? I get a torus. So there is actually a torus represented in your brain right now. So there we go. It has to be. So now I'm done with my sales pitch. Topology is clearly represented in your brain. There's a ton of ongoing research that suggests that many of the computations the brain do are actually topological in nature. So this is a big thing, and it's just starting up. Okay, so back to my grid cells. I've got this thing over here. I just want to tell you what I'm going to be talking about. I'm going to talk about receptive fields. So I'm going to take some subset of some Euclidean space. All right, that's going to be what I'm going to refer to as my stimulus space or my receptive field space. And I'm going to define a response function literally just to be a non-negative valued function on that subset. Okay, so this rectangle and that function. To each neuron that I'm going to study, I'm going to assign a response function of this form, and I'm going to take the receptive field just to be a super level set on that function. So there's the persistent homology, it's come and gone. If you're a neuroscientist or me, you're going to just ignore that theta and assume there are good reasons to choose that number to be what they choose it to be based on background noise and sensor difficulties and so on and so forth. That's science. We don't have to worry about that in this room. So I'm just going to take theta to be assumed, and I'm going to forget it's there. Okay? So the important thing, and you can see I'm lying right now, is that neuroscientists usually take receptive fields for neurons to be convex in the environment. There are very good reasons for this, right? If I assume that the neuron is attempting to map a location in space, then the neuron's response will fall off with distance to that point. If you do that, you automatically, for free, get convexity, right? So in the conceptual model that we want to put over the top of what these neurons are doing, right, representing location in space, convexity just comes in sort of as a free assumption. It doesn't work out that way in real data, but real data is extremely messy and may not actually be real data because there are a lot of confounds between you and what's happening in the system. So it's fairly acceptable, and it's also what the neuroscientists are actually doing. So that's what I'm going to do from here forward. Okay, so what have I got? I've got a bunch of convex sets that cover my environment. Unfortunately, I don't get to see those. Because if I don't know where the animal was, or I don't know that I happen to be looking at John O'Keefe's place cells, then this is what I see. And that is maybe not as understandable. So each of these horizontal traces is the activity of a single neuron, recorded in an area of the brain near the hippocampus, and I think there are about 40 of those up there. So each one of those little black dashes is an electrical spike on an individual neuron, putatively. The data is very noisy. And as you can see, there's wild variability between neurons, temporally, et cetera, et cetera. And the question we want to ask is, well, did this come from that receptive field model that I was just talking about, or is this something completely different, right? In other words, suppose that John O'Keefe never existed. We're in, alternate 2017 in a dystopian world without John O'Keefe. Then how do we know? How do we figure out what he knew? Or if I'm looking at an entirely new brain region, how do I know that that's a decent model to be thinking of when I don't know the behavioral correlate, when I don't know position is the thing I should be thinking about?
So this is a recording for 40 neurons at the same time?
It's about 40, yeah.
From the same animal,
Yeah, same animal, same place. Yeah, so this time in seconds is sort of a lie. I don't know exactly what this, I stripped off the the numbers, but each of those dashes is about a millisecond with event. So you can kind of guess the, all right. So I'm going to simplify this picture because that other picture is too complicated. So here are 4 neurons that I made up. And as you can see, they are nicely color-coded. And what you can see is that there's some sparse spiking events, and then there are these dense clusters of spiking events. And I'm going to go ahead and leave those terms undefined. And of course, you can just put your favorite persistence parameter in there, however you feel like doing it, or not. You can just take that to be a number the neuroscientists give you, because they know what they're talking about. So in that case, what's my data? Well, the sparse stuff is supposed to be noise, and then there are these weird little clusters of co-firing events. All right. So what I'm going to do is I'm going to take all of the pieces of information I needed there and sweep them under the rug, and just consider the co-firing events. Right? If you're really, really picky, you can think about individual neurons co-firing. Right? I can just think about every time that a neuron fires, looking at everything that's firing coincident with it, but that's probably a little too finicky for us because there's noise. So, all right, so I'm going to say the code of a neural population, a combinatorial code, but just the code from here on out, is just the collection of subsets of neurons that I observe co-firing. Okay, it's coactivity profiles. So here, right, 2 and 4 co-fired, 2 and 3 co-fired, and 1, 3, and 4 co-fired. So that's going to be the code that I observe in the population. Okay, and you can take the empty set or not. That's up to you. I'm not going to fuss about it. It's not going to change anything that comes after this. So, all right. So now the question becomes, yes?
Do you, if something fires and nothing else fires with it, would I want to include, say, 1 on its own if it fired in a chunk?
Yeah, that's right. So whatever parameter I use for picking out what the events are, it certainly is possible. I can have one thing or all things. Basically, code is my fancy word for arbitrary subset of the power set. But it's the one that I got back from nature, so I want to specify it. So then now I've finally formulated a question, right? So is it possible, given a combinatorial code, this one here that I saw, that it came from something like this, right? A collection of convex receptive fields. Okay, and you can see that this must be at least in principle kind of answerable, right? 2, 4 co-fire, what does that tell me? It tells me that over here somewhere I have a pair of receptive fields, and they have to overlap because both of the neurons were firing sufficiently much. Okay? And that feels a lot like combinatorial topology to me. And it's going to turn out that we're going to be able to use the tools of combinatorial topology to give us partial answers to this question, but they're not actually correctly built for the kinds of data that we're getting. So, all right. So, math talk, I have to give you a bunch of definitions. So, let's phrase the question, the inverse question properly, right? If I give you a bunch of sets, just subsets of my stimulus space, then the code is, well, it's the collection of atoms. So it's the collection of sets that are present at any point, right? So here, for example, just this individual, there's that yellow is not showing up very well. There's a set right there. So here's, this red is set 1, right? So there's a point in just set 1, so I'm going to go ahead and record 1 as a code word for the code. But 4 is entirely contained in 3, so I'm not going to record 4. I'm only going to record 3, 4, because it would be impossible for me to have neuron 4 active without neuron 3. Right, that's sensible. Right, so that's, and I just want to point out, right, that's different than the thing we normally use. Right, so here's the code for this collection of sets. If you're bored, you can check that. So, right, the thing we normally do is we consider the collection of all non-empty intersections, right, without throwing away this other stuff. So the nerve is a simplicial complex, and that's fantastic because we can do things like compute homology and all of our favorite things. And in fact, it's the smallest simplicial complex containing the code of the sets. So what we're going to write is that the nerve is the simplicial completion of the code. Okay, but the fact is that there is, so here, all I have to do, right, to specify a simplicial complex is to give you the maximal faces. That's going to be kind of interesting later. Right, but it's the simplicial complex with these maximal faces. So the fact is that the nerve contains less information than the code. And we know that because I just pointed it out, but right, the code tells me, right, so look, 4 is contained in 3. How do I know? Because code word 4 doesn't exist, right? 4 only appears in the presence of 3 in the code. Right, so if I have this code laying around, I know information about set inclusions, I know other information, so more subtle information, and this is sort of the more interesting bit. The code contains information about geometric features like dimension. So here is another collection of sets. My claim is it has the same nerve. It's easy to check, right? Look, 1, 2, and 3 all intersect, okay. And 3 and 4 intersect, okay, so those are the maximal faces. So this and this have the same nerve. But this collection of sets, this code, the code of this collection of sets, cannot be realized by sets in dimension 1. Is that clear to everybody? Because of this, right? I've got these sets all arrayed around this center point. Up here, I could just project this all down onto an interval. Everybody's going to be happy, right? But it turns out that if you write down the code of this collection of sets, there's something in there, and it's what's missing, not what's present, that tells you that there's no dimension 1 realization. Okay? And I'm going to tell you right now, I don't know what the missing thing is. I can give it to you in small cases, in specific cases, but the dimension problem is essentially open for looking at codes. Right? You get a nice bound by using what we know about simplicial complexes, right? Because I can always realize this thing in the dimension the simplicial complex is realizable, and I'll talk about that in a bit. But the code is a richer data structure. All right. And just before I move on, there's one other place where it's richer, and that is that the nerve is a fundamentally homological construction. Right? We build it so that we can understand the homotopy type of the space. The code is something a little different, and in particular, when we want to talk about convexity, there are going to be strong requirements that are not there in the case of homotopy. Okay, so this is our object of study. So I want to say that a code is open convex or closed convex if there is a collection of sets which is open or closed, which realizes that code. Okay, right. So I need convex sets sitting in my space so that when I sample them, I get the code back. That's a reasonable definition because it's the right answer to my inverse problem. So here's cautionary thing number 1. Closed and open convex are distinct classes of codes. I didn't know this when we started doing this, and the first few papers on this subject don't distinguish. We just assumed that open convex was sort of the best case and that closed convex was a subset. But here is a collection of closed sets. So it's these closed rectangles, right? This big closed rectangle on the left, big closed rectangle on the right, that thing, and these guys. That's a collection of sets which has a closed convex realization. And here's the code. Not that I expect you to parse it, but it's there. As far as I know, this is the smallest example. But if you try to realize this with open sets, something goes wrong. And here's what goes wrong. It's that this measure 0 thing right here thickens up. And no matter how you try to put convex sets in here, you end up getting an extra code word out of it. There's an angle issue that happens in the geometry. Okay. On the other hand, here are a bunch of open sets, so just think about these as half spaces that all meet at those lines in the middle, right? So I've got, the half space going off that way, the half space going off that way. Those are all open. So those give me some code. It's this nice symmetric code. And the problem is that when you try to close them, either you pick up that point in the middle, which you don't want, or you have to separate everything a little bit, and then you get all sorts of things you don't want. So, so there's very subtle boundary issues at play here. One can make a sensible notion of genericity. That would take me the next 30 minutes, so I'm not going to. But but there's a nice subset of both closed and open, which is characterizable extrinsically, that gives you a decent thing to use in the context of data. Of course, you don't want this kind of issue when you're dealing with actual data, because boundaries are something you're not likely to be able to measure. So nonetheless, from here on out, I'm just going to talk about open and closed convex codes and keep in the back of my head that they're distinct classes. Okay, so we finally have the question, right? I have a code. Is it open or closed convex? Yes or no? Right? If it is, if I'm observing neurons firing and I say, oh, that's a convex code, then it's sensible for me to be looking for a receptive field model and trying to solve the problem of what are the neurons representing from this context, right? There's a good model. And if they're not, then don't do this. So first thing that you have to point out is that there exist codes that aren't convex, either open or closed. So here's the smallest possible example. Didn't take us long to find this one, thankfully. Okay, so what's this look like? Well, I've got 3 sets. I've got set 1 and set 2, which appear on their own, then set 3, which only appears inside the other 2. Okay, so that's, imagine I observe that in the brain. Now I'm going to try to draw it. So I've got set 1 and set 2. Those appear on their own. They don't intersect because 1, 2 doesn't exist. So now all I have to do is draw set 3 convexly, such that it lives inside both of them but never on its own. Probably not going to happen. Okay. So why doesn't it work? It doesn't work because of the nerve theorem. So I told you there'd be some topology in here somewhere. Okay. So the version of the nerve theorem that I want is that I have all open or closed sets such that all intersections are convex. All right. In the open case, this is too strong. In the closed case, this is also too strong, but for different reasons. But this is the version I need, so it's the version I'm showing you in case there's a small chance that you haven't seen it at this point this late in the game. Okay, so assume that I have a bunch of sets and their intersections are all convex. And they're all either open or closed. Then the nerve, the simplicial complex I talked about earlier, is homotopy equivalent to the union of the sets. So why does that tell me that this won't work? Well, let's see. I have, let me look at the nerve of this collection of sets. That's a simplicial complex with 2 maximal faces, 1, 3, and 2, 3. Okay. So let me just take the set that I'm interested in to be 3, set 3. Right? The code tells us that that set is covered by U1 intersect U3 and U2 intersect U3, right? That's what the code is telling us. So if I look at the nerve, that's a connected 1-point set. But if I look at the union of the sets, I have 2 disjoint sets. So 2 points is not homotopy equivalent to 1 point. There can be no realization of this object. All right. So this obviously generalizes beyond this one simple, silly little example. So if I take a code and I look at what I'm going to call a simplicial violator, that is a subset of an existing code word which is not itself in the code, right? Something that can't be there if my object is a simplicial complex. Right, so I'm just going to take the simplicial completion of the code, and I'm going to look at an element that shouldn't be there. So then so what is that? That's a contractible set because it's an intersection of stuff, but it's covered by other things or else it would be in the code, right? That set has to be covered by other stuff or there would be a code word representing it. So I can look at the link. That link is a simplicial complex representing all of the sets that cover up the set that's missing. And of course, the set I've covered up must be contractible by hypothesis, right? In fact, it must be convex, but right. So I can test whether this simplicial complex is contractible for every single one of those, and if any one of them is missing, then there can never be a convex realization of my code. So I call that a local obstruction of convexity because you're looking at a single missing code word and using that to determine if things fail. We know that that's not the only kind of obstruction because of those two examples I gave you at the beginning, right? This tells me that there are things which can never be convex, either open or closed, right? The nerve theorem applies either way. But there are things which are open but not closed and closed but not open. So there are more subtle obstructions. Today, I'm not going to be able to give you any of those. That's essentially an open problem. There are a lot of open problems, and they're just right on the surface. Okay. So there exist codes that aren't convex. Let me take a little sidestep here and tell you a little bit about neural networks from a different architectural point of view that is related. So this is the simplest possible architecture for a neural network that does a computation. There's an input layer of neurons, an output layer of neurons, and connections from the input layer to the output layer. This is called a feed-forward neural network. It's called a one-layer feed-forward neural network because there's exactly one set of connections. Okay, so I have an input to an output. I could take a bunch of these and stack them, right? I could take another layer and put it below. I get a 2-layer network and a 3-layer network and a 14-layer network, etc. You take about 1,000 of them and you get a deep learning network and you make a bunch of money at Google. But I'm not capable of analyzing those ones, so I'm going to analyze this one. So the rule is that you take for each output neuron, you take an affine combination of the input neurons. Right? So I'm just going to take some affine combination of my inputs, and then I'm going to slam it through a nonlinear rectification function. So if this affine transformation the output is less than 0, then I'm going to just tell you it's 0. And if it's positive, then it's some positive number, and I don't care which one it is. So if you like, you can think of it as the Heaviside function. If you like, you can think of it as the linear rectification function, or you can just think of it as anything you like. For purposes of what's to follow, I don't care what it is. It just has to be some rectification. Okay? So it turns out, and this is well known for quite a while now, that this kind of network corresponds to this kind of geometry. So what I'm asking is, I take an affine transformation of a vector, right? Or right? So I plug it, take a vector, I plug it into an affine transformation. This is dot product with another vector. Sounds like I'm checking to see whether you're on the positive side of a hyperplane. And then I'm saying if you're on the positive side of the hyperplane, then you're on, and if you're not, then you're off. So what I have is for every neuron in the output plane, or in the output layer, in the output neurons, this thing is called a layer, and this is a problem in the terminology because people also call this and this a layer. The thing in red is a layer. Okay, so each one of these planes and corresponding half spaces is an output neuron in the input space, which is given by the collection of input neurons, right? So and of course neurons never take on negative values, so I'm only looking at the first orthant, right? So I look at the first orthant of R, or whatever this is, and each neuron gives me a half space. And now if I'm in, say, the positive side of neuron 1 and the positive side of neuron 2, then I'm in this region, and I get code word 1, 2 back, right? Because those are the neurons that are on. So this gives me, lo and behold, a collection of convex regions, each of which is assigned a code word. So these one-layer feed-forward networks are an example of a system which would produce a convex code. Right? So again, if I have non-convexity, then I know that this is not the architecture that I am looking for. But we can do better, because unlike in the case of regular convex sets, where if I delete one from another, convexity goes away, here I have half spaces, and deleting a half space from a convex set gives me back another convex set, right? Just lop off everything on this side, and what's left must again be convex. So what we can say is that I can look at any subset of the neurons, which corresponds to just lopping off the active regions for the other neurons, and I must again be convex. So this is a much stronger condition. There are a lot of subcodes that must be convex in order to get this kind of realization. So the theorem here that is nice is that, So let's see. So you think, okay, that sounds really restrictive, but if you give me any simplicial complex of your choosing, just choose your favorite one, then I can build a non-degenerate, so a generic, in the sense that I can wiggle the planes, feed-forward network, so that the nerve gives me back the original simplicial complex. What it means is that I can build a neural network like this, which hits all of your maximal faces and then maybe some other stuff. Okay. And that was really counterintuitive to me when I first learned it, because this is supposed to be the most restrictive, simplest, dumbest neural network you can build. But you're often, when you're thinking about real-world applications, you can't be worried about subsets of faces because that's too sensitive a thing. Right? I really have to be worried about the maximal faces in my complex, right? Can I turn on this collection of neurons? Can I turn on this collection of neurons? Can I turn on this collection of neurons? It turns out that this silly little architecture here can do that for any specified simplicial complex you like. So this is a little disconcerting if you think that the brain has a reason for being complicated. So it turns out that what this really tells you is that that complication needs to be involved in things like dynamics and storage and so on and so forth. It can't just be involved in input-output relations. So here's a nice conjecture, and if any of you wants to prove it, then I'd be happy to see that. The thing I just said a few minutes ago is the whole story. So there's one. I want to know what are the obstructions to building this network, right? If I give you a code, can you build this network? So my conjecture is the following. I should say Vladimir and Zvi Rosen and I. So I'm going to take a code, and I note that for any given code, I can let the group, I'm going to call it G2 to the n because C is taken, or Z2 to the n, acts on that code essentially by just inverting, right, the nth, or the kth factor inverts whether or not element k is in any given code word. Okay, so I can act on a code with this group by flipping in and out elements. Okay, what does that involve? What does that tell me to do? It tells me to swap the positive sign in this geometry, right? If I hit this with the first group element, the first non-zero group element, then the positive side of this plane is going to pop over here, and I'll get a 1 there, and a 1 there, and a 0 there, and a 2 there. Okay, so that's a perfectly valid hyperplane geometry. So this new code that I get by hitting you with my favorite element from that group must also be a hyperplane code. It must also be a feed-forward code. So, but the claim is that all you need to look for are local obstructions, the ones that I told you about earlier, because this is such a restrictive class of codes, on that collection of reflection codes. So we've yet to find a counterexample to this, and we've done some searches in some very large spaces using computers. So I think this is probably true. All right. So the upside of this is that you say, okay, well, nobody actually cares about this one layer stuff outside of its theoretical interest, but these are building blocks, right? Like if I understand how these things compose, and it turns out that people have done some interesting work figuring out how these things compose. Right, 2-layer networks are universal function approximators. 3-layer networks can sew together any binary algebra, or Boolean algebra on convex subsets of the plane. So you get a lot of really interesting data out of this, but the problem is that we don't know what the building blocks actually do. So, all right, so please go home and prove this. All right. So, all right, I've showed you a lot of non-convex codes, but I do want to tell you that there are some really useful convex codes, and they're actually similar to the ones we just saw, but I can do them in a much more general sense. So, I take a code, and I take its maximal code words, right? So again, these are the faces of the simplicial complex. Right? These are the sort of the facets of the simplicial complex. These are the things that I care about from an applied standpoint, usually. Okay. And I'm going to take those objects, just the maximal faces. I'm going to take the intersections of all such. Okay. So it turns out this is a simplicial complex, right? Because I'm just taking intersections of of sets, and I'm taking all the intersections, so I've got closure under intersections, closure under taking subsets. So, okay, so if the code contains this mess, this new simplicial complex, then we say it's maximum intersection complete. Name we made up for it. And the reason we made up that name is that it turns out that if your code happens to be maximum intersection complete, then we can also, it's also convex. Okay. And this is, again, fantastic, because it actually essentially tells me that any neural network I observe in nature should be modelable using these convex receptive fields. Why? Because I can't care about the noise. I can only care about the big chunks. I can't observe, maybe 20 years from now we have better neurotechnology. We can do this. And that, in some sense, tells us that neural computation can generically be thought of as doing this, as putting convex sets in some space. And there's growing experimental evidence that that is basically a fundamental computational chunk. In other words, there are regions of the brain that do exactly this, including the hippocampus, which recently, very, very beautiful experiment recently showed doesn't just do this for place or time, which we knew in the 90s, late 90s, early 2000s, but in fact it does it for everything. So when I say everything, I mean they tried it on something so dumb that there's no way that we actually have hardware to do it, and discovered, again, convex receptive fields. Okay, so. And all right, so I'm going to finish up here with proof by picture because it's just after lunch and you're all looking tired. But the point is that these maximum intersection complete codes. So this is what I just wrote down what I said. Okay, so let me think about the simplest case that I can draw, which is a case where I have exactly 3 maximum code words. Okay, so then this maximum, and I'm just going to let the code be the intersection completion of those code words. Right, so I'm going to put in all the intersections of those objects. And now I want to build for you a collection of convex receptive fields which realize it. So I'm going to start by taking, and the theorem said I could do it in dimension 2, which is 1 less the number of maximal code words. So here's my dimension 2 best possible hyperplane arrangement, right? So you can always get hyperplane arrangement that has the right number of chambers. That's a basic combinatorics fact. And now I've just got to assign these code words to regions in a compatible way. So, all right, so let me just assign, right, so I've got to be symmetric here. There's no sense in being not symmetric. So I could put sigma 1 here, or I could put it here, but there's nowhere else to put it, really, and everything else follows. So if I put sigma 1 here, that tells me that some collection of neurons are on in this region, and some collection of neurons are on in this region, signified by the code word sigma 2, right? Well, now I've got further forced information. So, right, if a neuron is on here, and it's on here, and I want the receptive fields to be convex, then it better be on all the way through here, right? So what has to go here? Well, sigma 1 intersects sigma 2, right? All the neurons that are on in both regions. Okay, so now the rest of this fills itself in by necessity of convexity. Okay, and lo and behold, there is a hyperplane code, a half-plane code, that realizes this object here. That's not particularly surprising because, as I told you, it's a simplicial complex, and the previous theorem told me that if there aren't, right, that I can always realize sufficiently nice in particular simplicial complexes. But I told you I could do this with any maximum intersection complete code, so I should be able to add other stuff back in here and right, other code words that aren't necessarily these guys, right, that aren't intersections of maximal code words. So let me just tack on a new code word. I'll call it tau. And tau is not one of those, so, and it's not a maximal face, because if it was, it already would have been up here. So it's a subset of something, and I'm just going to choose that. So I've got tau is a subset of sigma 1 intersect sigma 3. So I'm going to look down here at the region where sigma 1 intersects sigma 3 are located. I'm just going to draw a giant circle around the whole code and intersect with it. right? So now I've got an outside boundary, and I'm going to take a spherical chord, right? If I chop a spherical chord off of this region, it's going to remain convex, and so is this. So I'm just going to take all the things that are in sigma 1 intersects sigma 3, but not in tau, and just nudge them up that way. And now I've uncovered tau. And now I can do this over and over and over and over, and I can fill in as many code words as I feel like filling in, because every code word that I want to add is going to be a subset of something that's already there. Okay. And as you can imagine, if I increase the number of maximal code words, this argument does not get any harder. So this is a simple, straightforward, constructive realization. So I can actually now take this geometry and test it. It's going to be wrong because it's one choice of realization. Yeah.
So what if I had tau 1 and tau 2 both in that same subset?
So I would just hack off another, I would make this one smaller and hack off another spherical chord, right? I could also, right, so sigma 1 intersects sigma 3 is definitely a subset of sigma 1, so if I decided I was out of room, I could also put it over there, right? Yeah, the point is you start with your, you start by taking your list and then just divvy things up. Then it would also be in every other intersection.
So we could just put it anywhere else.
Right, I just have to choose some superset of tau, right? So, yeah, the only thing in the middle is the intersection of everything, and I already know that that's, I can work outside of that, so that's sort of our special case intersection. All right, so that's the whole generic thing, and that's, I'm a little bit ahead of myself here. So yeah, we have a couple papers. First one talks about the feedforward geometry, and the second one talks about all of this stuff about convexity. There's some other results about monotonicity of constructions and so on and so forth in there. So thank you.
I have two questions. So the first one is very suggests itself. So when you have a code, what's the complexity of deciding whether you have a convex realization or not? Is that anything complete, or?
Well, as of yet, we don't really. I mean, so what can I say to you? I can say that in this particular case, we always have one.
Sure.
But yeah, there's right. So if you want to use this, if you want to find obstructions using this, right? You're checking contractibility of a simplicial complex, which is undecidable. On the other hand,
That doesn't mean much. Sure.
right?
This is an NP because you can just guess the convex sets and check. So it should be at least, it should be not harder than NP, right?
Yeah. Okay. So yeah, if you guessing the so I guess you could try all possible arrangements of convex sets. That seems about. I mean, right? You never have 3 or 4. You have 40 or 100 or 10,000, which is currently the state of the art. At that point, right? Anything that's not linear is not doable. So.
And the second question, you always restrict to open or closed.
Yeah.
But if your counter example, if you don't have any restriction, if the sets can be half open,
Yep.
then this
Then-
counter example will not work. Right?
That's right. Yeah, then you can just. So, yeah, right. There's a really simple drawing, right? I take one of them to be closed and one of them to be open here, and then I just draw, right? So that's 1, 2, and 3. Right, I just smush the boundaries together. Everything works out just fine. So that's correct. But you shouldn't have to distinguish boundary openness or closedness in any neural system, because the fidelity is too high. Right? The neurons are firing in a noisy system. They're trying to decode from upstream when they don't know what the thing they're decoding is. So at least in the brain, choosing open or closed is wrong.
Okay, but if we just a theoretical question, is there a counter example for the general case?
Not that I know of. So, okay, well, hang on, just give me a second. Convexity in the general case. No, I don't know of one. And essentially because I think you can always play this game where you take your missing code words and you sort of smear everything else up. I should also point out that one of the other reasons why I know this isn't the whole story, besides the fact that we have examples, is that we've checked a homological condition, and the thing that we're demanding is convexity, right? And I stated the nerve theorem as being about convexity, But in fact, the nerve theorem is about contractibility. So this whole obstruction is somehow too soft, right? We can't possibly see all the bad things.
Questions? Well,
Right.
not this, thanks.
Thank you.